Thank you everyone for joining our webinar this afternoon. It is choosing the right rotary die cutting setup. It'll be a 20-minute presentation by Saria and Paul, and then we'll have question and answer after that. Our session will be recorded, and we will send out a recording of the presentation to everyone either later this week or early next week. Our agenda is starting today. So how many process stations do I need? What requires a dedicated station? How do materials affect processing? What effect does the part construction have? How do I choose? And then some real world examples. I am Quinn. I'm the marketing manager for Preco. I graduated in 2004 and I've been here, excuse me, since 2009. Saria joined us in 2023 as a Rotary applications engineer, and he helps Preco customers find their right Rotary based on solutions for them. He holds a master's degree in mechanical engineering from Miami, and has prior experience with experimental design, additive manufacturing, product development, and teaching. And Paul is the Rotary product manager. He's been in various manufacturing roles over the last 20 years. He has very extensive knowledge in the rotary die cutting and laser processing of flexible webs. He worked in contract manufacturers of medical devices before the Rotary applications engineer in 2014 and became the product manager in 2019. So I will hand this over to Saria and Paul
now. Hey, thank you, Queen, for introducing us. Hello, everyone. Thank you for joining the webinar. So today we'll discuss about what does it need to determine how many stations and spindles you'll need for the process for a rotary converting platform for your various applications. In this webinar, we'll be learning about various type of stations in a rotary converting platform. I'll be coining it as a RCP, rotary converting platform, along the way. And why do we need those stations, and what kind of materials or product features that dictates on requiring these stations, and how big of a station do we need for our process, and how many spindles do we need for the process. So we'll be talking about a lot of those things, and then we'll be concluding with some real world examples. So let's start with first learning about like what kind of so what are all the stations and all the spindles. So right here, it's one of the rotary converting platform. So it has 5 stations and a lot of spindles right here. And let's dive into it with a part. So here is a product that has like features inside and out. And normally we can die cut it with one punch. So to make this part, let's do it in a proper way. So how do we do it? We need a nip station to control the progression of the web, and we die cut the inner holes, and we nip the web again, and we die cut the outer profile. So some might be thinking like we can do it with one punch, so why don't we do it with only one die? So we are doing this because on the first die cut, we can die cut the inner holes and take out all the slugs. So we'll get 100% slug removal in our part. So this will require like 1, 2, 3, 4 stations, including the nip station and die cutting stations. So this would be the good rotary converting platform for this one. So we'll be going through like what kind of stations do we need, and all of the other factors that will play into it. So let's start with some examples. So here are some example parts that you might come across, and you might need to do it on a rotary converting platform. So here is an example like paper handle that you can do it on a rotary converting. It requires a lot of lamination, folding, like loop forming, die cutting, and glue, a lot of things. And here's another one that requires some die cutting internal part, that requires die cutting, and the external part that requires heat sealing and die cutting. And here is another one that that has some high bond adhesive in this one. And this part is like you can so because it is a high bond adhesive like BSB sample, you might need a laser cut because the BSB will stick to the die. So laser cutting all of these features, and there's then die cutting the whole part afterwards. And this is a simple part that we talked about previously. And here is another one that requires assembly into the product. So all of these little dots that can be assembled. So these are all the things that you can do it on a rotary with like various kind of applications. So what requires a dedicated station? So here are some of the processes that requires dedicated stations for them. The processes are like lamination. Here, the lamination is happening with all of those webs going into the nip station. And then here is another one, die cutting. So all of the like features are shown right there. Seating, if you need to seat a part. Slitting, if you need to slit some lanes, like one web into multiple lanes. Heat sealing or cold sealing, if you need to heat seal some product with some part inside, then you need some heat sealing or cold sealing. Island placement, so island placement, if you need some part to be assembled after cutting, and you might need them in a different repeat in a web or something like that, then you can use island placement unit. Laser processing, you can also use integrate laser processing in a rotary converting platform, and it will also require like some dedicated station space. So flexographic printing, you can also edit into a rotary, and then all of these flexographic like the flexographic printer will also requires a dedicated space for the process. So besides this, there are other factors like materials. So how do materials affect processing? So some special materials might require extra stations that will need to be implemented for the process to be better. So for example, if you have a stretchy material, then you might need a low tension spindle, a dedicated station to let out all the tension in the material to release the tension and then get a good part. So sometimes if you have strong adhesives, then you might need to strip the strong adhesives using some brute force. So you might need a differential spindle, or you might need like a station that can strip the adhesive properly and then fit it to a spindle or any other waste collection unit. The sacrificial liner or tape might need another extra nip station, so that you can laminate that sacrificial liner to your adhesive layered some web. So soft materials, you might need some extra nips to take out the waste matrix of the soft material, so that there is like no breakage on the web while you're running. So those kind of things. And then on the soft material also, you can also apply some gauge pins to a station to release the tension and better tracking. And sometimes you, while doing some adhesive applications, what you might require is like corona treatment stations, so that your weight surface energy will be higher, and then there will be much better adhesion to your lamination. So these are all the factors that might affect whether you need a extra station for that specific requirement or not. And there's another factor, the part construction. If you have more complex part, So if you have a number of materials that go into your part, then you might require more nip stations to control the progression of all of the webs. So right now here you can see like 4 webs making a part. So you might require 4 of the different nip stations to control the progression, and then sometimes you can use one station to take like 2 of those webs together also. And another thing is like part geometry. Part geometry also, if you have like a lot of features on your part, then you might not be able to take out that feature in one station. You might need to add another station. So those kind of features also you need to take into account. And the part tolerance, if you need a very precise or very tight tolerance, then you might need to add extra nip to control the progression of the whole web, so that you can cut it properly and then register it properly to the registration mark. So waste or trim metrics, like we talked about before, if we have more waste metrics for like multiple webs, then what you might need is like you might need extra power nips, or sometimes roll feeds you need to add, or you might need to add like extra spindles to your process. And if you need to do lamination or delamination, then like a lot of webs going into one place, you might need to add extra station. Iron placement unit we talked about before, and the packaging also requires a dedicated station. So all of these factors, all of those variables we discussed previously will dictate the size of the system you will need. And for a rule of thumb, so you might see like how do I choose like what kind of things that I need to consider. So the rule of thumb, like it's a simple rule that you can take to determine like what kind of system you need. So for 1 to, if you have in your part like 1 to 2 die cuts, then you can use a small system, so a small RCP, and it will have like 3 stations, 6 spindles, RCP. You can use it to get away with your product. If you have 2 to 3 die cuts, or you want to do limited packaging, heat sealing, or cold sealing, then there's some medium unit that you can use. And all of those like extra station might help you out. And if you have like 3 to 5 die cuts and you want to do like limited like the packaging, heat sealing or cold sealing in your packaging, then you might need a large system. So these are the standard system that you can use while choosing like what kind of part you need to make. And it's not limited here. So there are other things like custom systems you can make, like huge systems. If you have a lot of features, you might only want like one station that only cuts, like it doesn't need any registration or something like that. So there are always custom systems that you can use. So this is how we can choose a rotary convection mechanism. Now Paul will be taking us through the case studies. I'll give it to Paul.
Okay, thank you, Surya. Hi, I'm Paul, and I'll review these case studies with everyone. Let's say a client asks you to convert or finish label stock for them. That's usually a very simple rotary process and a good one to understand the dynamics. So to choose the correct system, you need to gauge the input outputs, the tooling, the tolerances, and the run rate. With a registered to print die cut, you'll normally see a controlled tolerance of 0.5 millimeter or 20 thousandths of an inch. And And then that should allow you to run the process between 200, 250, maybe even 300 feet per minute. So if we look at the criteria here for this label stock, we want to make 2 million of these per week. And at that 200 to 250 feet per minute, that's probably 4 or 5 production days. Do we have any sacrificial liners or masking? Not with label stock normally. What are the input rolls? So we talked about having a printed roll that we'd be bringing in. So there's just a single input roll. And then there's 2 output rolls. We have the finished labels on the liner, and we also would have the scrap matrix to take up. So that's 1 die cut. And the type of material we're looking at, rubber-based adhesive with a silicone-coated liner, something like that along those lines. So as we dive into the part construction of a label, we see the printed logo here on top with a registration mark for controlling the pitch. And then on bottom, we have the finished label where the waste matrix has been stripped around the part from either edge and between the labels. And this allows the label to be dispensed appropriately for application. So when we choose the rotary system for this part, we need a small rotary with 3 die stations, 6 spindles. So we have the input roll of label stock there on spindle number 4, which would enter the first die station, which would be a nip roller to control our tension and our progression of the material through the process. Then the web would go pass underneath a sensor to read that registration mark. There's a variety of sensors out there. So sometimes they're optical, laser, through beam sensors, whatever fits your product. From there, the web enters the die cutting station where we're kiss cutting the label to the release liner. The waste matrix is wrapped around the tool and taken up to spindle number 1, which is a common practice in rotary processing. From there, the material enters the final die station, which is another nip to control our tension and progression. This helps us maintain part size. As the tool's cutting the web, we have very finite control of web tension, inbound and outbound. From there, the web is rewound onto spindle number 6, and you have your finished roll of labels. You can see even with this process, we don't utilize all of the spindles. And one of the nice features that there's just abundance of spindles for the machine. So for the next case study, we'll look at a medical patch, which is a little more complicated. So I'd expect a little bigger control tolerance for this part, maybe in the 1 millimeter plus or minus range. And then our processing speed would probably be more in the realm of 25 to 50 feet per minute. So we need to evaluate the number of layers going into the part construction, the scrap rolls that we'll create, the number of tools required for the process and the cutting, and then the finished rolls as our outputs. So as we answer these questions, it helps direct us towards the appropriate size rotary system. So for the volume on this one, we need to produce 70,000 medical patches, and that should be easily accomplished in that process speed. Do we have sacrificial liners or masking? We're going to have 1 sacrificial release liner in this process. How many input rolls are there? There's 4. So in the upper left corner, you can see the individual layers identified. How many output rolls are there? There's 5, and we'll see that in the next slide into more depth. There's 2 die cuts that go into producing this medical patch. And then we have our input materials are the silicone PSA, the double-sided acrylic foam, let's say, and then silicone-coated release liners. So as we look at those webs as they enter the machine, the rotary processing, the first portion is the through cutting of the holes. along with kiss cutting scoring the foam up to the top release liner. And this is to create our easy peel tab on the part. The second stage is to laminate the multiple layers together, creating that construction. And then the final stage will be to register and cut the patch geometry to the release liner for the final part. So on this process flow diagram we have here, we chose a medium RCP. We have the foam in the upper left corner on spindle 1 being unwound, and then our sacrificial release liner being applied to it. So at station number 1 is our lamination point. We have a nip applying the pressure and creating the laminated structure. Then as it progresses, we enter die station number 2, where we have our tool cutting up from the bottom so that we can score the material and remove the foam and the release liner from the edge. And then we have a ID cut, which is being vacuum extracted from the process. Down below, you see the 2 waste liners, and that's so that we can wind both of those waste matrices with the proper tension. So we've separated them and utilized 2 spindles for that process. In the third station, we're bringing in the silicone PSA. It has a release liner that needs to be removed from one side and to expose the adhesive. And so you see a double nip stack. The material wraps around and is laminated to our construction. We also have our new release liner brought in from spindle 9 into that same station. So we're laminating the three layer construction. As the material progresses, we have a registration sensor to read that ID cut. And then in the next station is another nip station to facilitate control of the tension and material progression once again. Finally, we have a tool to kiss cut the patch down to the release liner. We strip away the waste matrix up to spindle number 4, and we take the finished roll down to spindle number 10. And due to the thickness of this product, we did not use a 3-inch ID core. We expanded it to a 6-inch core so that when we begin a roll of product, we don't have displacement of our parts on the liner. So they stay in position, and that's a benefit of just knowing your materials and your process. From here, watch a short video of that process. We have our foam being unwound, laminated to the release liner in the first station. Here's our tool with slug ejection and the matrix, the release liner is being stripped away. The silicone PSA is being brought in, release liner removed, laminated to that construction, a sensor to read that position of the ID cut, another nip station, and then finally the pattern cut to the release liner, waste matrix removed, and your parts are completed and wound onto the final spindle. There they are on a 6-inch core. That completes the case studies.
In this webinar, we learned about various types of stations in a RCP and why we need those and what kind of material or product features that dictate on requiring these stations and how big of station do we need for our process. And we concluded with some real world examples. Thank you everyone for staying throughout the webinar. Yeah, if you have any questions, open for questions and answers. Thank you.
Perfect. Thanks, Surya and Paul. And we do have some questions. So if anybody has any questions, you can go ahead and type it in the Q&A bar at the bottom. So we'll start with the first one that I have, which is, can stations and spindles be moved around?
Yes. Yeah, thank you for the question. It's a good question. Yeah, all the spindles and the stations can be moved around according to like what you need. And you can also take out the stations, some stations, if you don't need them for a certain amount of time so that you have extra room. So adding any extra station or spindle Yeah, that's possible. And
So a spindle with a web guide, maybe you want to relocate it from spindle 1 to spindle 4. Those can be moved and then utilized in the new location. And as Surya described, removing a die station allows you to add, maybe you have a application device that you need to put into the process. You can add in those auxiliary devices and implement those as needed.
Perfect. How large of a diameter material roll can the spindles hold?
Yeah, normally for a general kind of setup, like general kind of rotary, 20 to 21 inches would be a biggest one, but like there can be a bigger, like you can add make some custom things so that you can include like huge rolls, maybe 40-inch diameter or maybe more than
even up to 5-6 feet. We could have a spindle just sitting outside of the rotary, and you can add a rotary or an unwind that has the capability to unwind massive rolls of foam that become very large. So
what is the largest system that Preco has ever built?
There's the largest system was like 20 stations. It was a huge system and no spindles. So it was an interesting one, like with no spindles.
So the requirement there was to keep the rotary machine in operation for an 8-hour shift. We integrated auto splicing turret unwinders so that material can be loaded, spliced in without the machine stopping. And how we facilitated the waste, we had to slit some materials and remove trim waste from either edge. So we put a nip station up high on the frame, brought the trim waste through the nip station, and then used vacuum extraction to take it to the granulator for it to be chopped and collected. So that really facilitated nonstop operation and was a very neat system. Yeah. But we can go bigger than 20 stations, most definitely. Whatever the application requires, we'll customize the system to your needs.
What is the maximum speed the rotaries can run at?
Generally, the rotary the maximum speed is like 300 feet per minute. But sometimes like with a bigger system, like wider systems, if you have like a 16-inch or wider system, then the inertia can play out on those kind of things. And then those things will like for that, you have to speed down your rotary process. So 150 for larger systems, I would say, and 300 for like systems that are less than like 13-inch width. Yeah, that can handle 13-inch width.
Yep. Yeah. And Preco builds 16-inch, 20-inch, 24-inch, and we can go slightly larger than that, but that's kind of where you top out on rotary processing usually.
All right. So next question is, for the first case study, did you say tolerance is plus or minus 0.5 millimeters at up to 300 feet per minute? And for the second case study, plus or minus 1 millimeter at 25 to 50 feet per minute?
Yeah, that's just a general tolerance that I was putting towards that product to evaluate the production speed and look at the volumes. And each process is unique. So tolerance, control of the machine and the input materials is always evaluated for each individual rotary process, but those are some general tolerances, yes.
Okay. Can you further explain island placement?
Island placement is like whenever sometimes in your process you might need to cut some parts, and then without dispensing those parts from that station, you might need to add it in line with the process to another web. So what you do is like you cut the part, you just grab the part with a vacuum anvil, and then you drop the part down to another web.
And that mitigates your material waste.
Yeah.
So you're cutting the part in a very tight pitch, maybe even common rule. And then when you transfer it down, you increase the pitch so that you don't waste the expensive material.
Does that answer your question? Yeah. Yeah.
We'll see if they reply. Let's see. And that's all we have for questions right now. I'll give it another minute or so if anybody has any other questions that they would like answered. Otherwise, if you do have any questions that we didn't get to on here, or you think of something later, feel free to email Saria or Paul or both of them with any questions that you have, and their contact information will be sent out with the recording of this video. So as of right now, we don't have any other questions. So thank you everyone for coming.
All right.
Thank you, everyone.
Thanks.
Yeah.